So last time we went over some features of metals, non-metals, and metalloids, and figured that they're quite different in their physical properties. And here are some elements that can be found in the human body. You will need to know actually just 4 of them. Okay. By the way, the new study guide is already posted. So this 4 elements, oxygen, carbon, hydrogen, and nitrogen, they comprise basically 96% of the mass of the human body. I don't really care about 96% number. You just have to know that these 4 elements is the most of the human body. Not going to ask you what the macrominerals are, but knowing that oxygen, carbon, hydrogen, and nitrogen are practically, most important ones necessary. So let's talk about the structure of an atom, and let's give ourselves some definitions. So atom is the smallest particle of an element that retains, and that's important, retains the characteristics. When we say characteristics of an element, of course, refer mainly to chemical characteristics. Atom means indivisible. Okay, so that's hence the name. So the British scientist John Dalton formulated the atomic theory in which he proposed that atoms in the same element are similar to each other. Not just similar, they are almost identical. It can be some variations, which we're going to cover. They're almost identical. Yes?
When did he propose this theory?
Late 1700s, I want to say. I mean, the idea of atoms it originated in ancient Greece by Democritus. Democritus? I don't know how to properly pronounce the dude's name. But it was like Anaxagore, Democrit, those guys suggested that there were atoms, but they suggested a lot of other pretty crazy shit, which we didn't accept since then. But Dalton actually proposed not philosophical, but actual scientific concept of this. So, when 2 atoms are combined, they form a compound. I mean, not necessarily 2, you can combine 3, 4, like sulfuric acid, 3 different kinds of atoms. And in chemical reactions, atoms are rearranged. So let's say, I had one question on the exam today. There was a statement, when you heat up the, sodium hydrosulfate, it produces sodium sulfate in water, something like that. I don't remember exactly. There was just a statement, in one of the answers. So in this case, atoms are being rearranged. And you get one compound in the beginning, you end up with 2 different compounds in the end. Now, one important statement, which seems absolutely trivial, is that atoms cannot be created or destroyed in chemical reactions. And that's important to know, because here we're talking about chemical reactions and nuclear reactions, like the ones that happen when atomic bomb explodes or thermonuclear bomb explodes. In those reactions, new elements, new atoms are created, or some atoms are basically destroyed. Does that make sense? So atoms, during chemical reactions, atoms are only rearranged. Never created, never destroyed.
And you're saying during an explosion, they're just
Rearranged.
They're just rearranged.
During chemical reaction, any chemical reaction. So hold on. During any chemical reaction, atoms are just rearranged.
Right.
If you would look at the nuclear reaction, like nuclear explosion, you will see that some atoms become completely different ones. So you start with hydrogen and you end up with helium, for instance. Okay? Now, in chemical reaction, if you start with carbon and oxygen, you end up with carbon and oxygen. Nothing new, nothing new appears, nothing disappears. Am I clear? Yeah.
I have,
In order. Go ahead.
so are we saying that nuclear explosions, for example, they're not considered chemical?
Absolutely not. Those are not chemical reactions. Eugene.
Okay, so, in the chemical change, let's say last time you make examples of burning wood,
Mm-hmm.
and then so when the wood burning, it create different type of like
Compounds.
you know, yes,
Yes.
compounds. But the atom, it's still the same.
Let's put it this way. Let's suggest that wood is cellulose, which contains carbon, hydrogen, and oxygen. When you burn it in oxygen. So you have three types of atoms: carbon, hydrogen, and oxygen. Does that make sense? The products will be carbon dioxide and water, containing same three types of atoms. You don't get nitrogen, you don't get phosphorus, you don't get sulfur, all those same three types. Does that make sense?
Okay.
Got it? So basically, medieval alchemists that try to, I don't know, take some crap like urine and get gold out of it, it would be impossible in chemical reaction. That makes sense? Because it's just not enough. No gold in the urine. Atoms consist of three types of particles. Protons that have positive charge, electrons that have negative charge, and neutrons that have no charge at all. Positive charges repel, negative charges to each other repel, but if you take two different charges, positive and negative, they will attract. That makes sense so far? Now, skip this. I forgot to just skip. We're not going to talk about the Thomson versus Rutherford model of atom. For our intents and purposes, we will think about an atom as the nucleus in the center. Does that make sense? And electrons circling around the nucleus. Am I clear? So nucleus is in the center, and electrons are circling around like planets on the orbit. That make sense? Each atom has a mass, which is, you can measure it in grams, okay? But it's super, super small. Like, I don't remember, it's just super small, like 10 in the negative 24 grams, something like that. So like ridiculously small, okay? So, instead of grams, we use atomic mass unit, or AMU. That make sense? In scientific jargon, atomic mass unit, sometimes you can find it, is referred to as Dalton, honoring that fella, the scientist that proposed atomic theory. That makes sense? So the definition of the atomic mass unit is if you take an atom of carbon, not just carbon, but the particular isotope of carbon, we're going to talk about isotopes, so-called carbon-12, and you take 1/12 mass-wise of that carbon atom, that will be one atomic mass unit. Does that make sense? I want to explain. Atomic mass unit is the unit of measurement that was introduced for convenience. Does that make sense? Now, what about the masses of those particles? Pressing question. Do you need to remember these actual numbers for our purposes? The answer is no, not really. what I want you to understand is that both proton and neutron have a mass of about 1 atomic mass unit. Does that make sense? So they weigh approximately the same. Am I clear? Second statement that I want you to digest is that electron is incredibly small. You see? It's in 10,000th of atomic mass unit. So my question is, when you look at any atom, which particles will contribute to the mass of an atom almost 100%? Protons and neutrons, because they're really, really heavy. Electrons, no matter how many there are, they do not really contribute to the mass of an atom. I mean, they do, but we discount them because their contribution is so small. Does that make sense? Awesome. So that's kind of a summary that shows you the location. Both protons and neutrons are always a nucleus. Mass, again, do not memorize the actual like 1.007. I don't see any real benefit in that. You do need to know the charge. We'll ask about that. Okay? Symbol, just know it for convenience. Okay, because we're going to use these symbols when we're going to talk about nucleus. We're clear so far? Good. So, what you need to understand is that all atoms of an element have the same number of protons. Let it sink in for a second. So if you take carbon, all atoms of any carbon that you will find in nature, they will all have 6 protons. That makes sense? 6.
Electron.
So we'll get to electrons. So far, 6 protons. Okay? Does that make sense? Which means that they all have the same atomic number. Now, if you will go to, well, if you will go to the, what should I call it? Sorry, here. So that's, I don't know if, oh, you can't see it. I always forget that it doesn't work this way. So if you will go to the periodic table, you will see next to each element there is an atomic number. Okay, like hydrogen is number 1, helium is number 2, lithium is number 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and could never remember neon. Never could remember the order of noble gases. Whatever. That makes sense? So this atomic number represents the number of protons in an atom. This is really, really important. Does that make sense? So if I tell you that the atomic number of, one thing that came as a surprise to me is that sometimes in high school, students are forced to memorize periodic table. Just like memorizing Google, really. I tell you that atomic number of nickel is 28. What does that mean? That nucleus of nickel atom has 28 protons. Does that make sense? It's always written above the symbol. More frequently, like if you write down, say, carbon, it's going to be carbon, and the atomic number will appear. Nope. Nope. Here. Okay, in the periodic table, it's written up top.
We didn't see anything. Oh.
Here. Okay? Does that make sense? Now what's important is that atomic number is the same for all atoms of an element. Now, those are some examples. For hydrogen, atomic number is 1, which means every atom of any hydrogen has 1 proton. For carbon, it's 6. For copper, it's 29. So every copper atom has 29 protons. So this illustrates that concept in the picture. For instance, in lithium, okay, the atomic number is 3. Therefore, lithium has 3 protons in the nucleus. Protons here are shown in red. Does that make sense?
Mm-hmm.
For carbon, red particles, if you count them, there are 6 of them. So that's the atomic number of carbon. And before we get to them, we're going to talk about mass number next time. You have to understand that atoms, by definition, are neutral, which means that in an atom, the number of protons and the number of electrons is the same. So protons are charged positively, electrons are charged negatively.
So
There-
the proton and the electron, they're always the same number.
For an atom, yes. There are different kinds of particles for which this rule doesn't work. But for the atom, by definition, is electrically neutral. So number of protons equals number of electrons. So if atomic number of carbon is 6, how many electrons does it have? 6. Is that clear? Awesome. We're going to continue this chat on Monday.